Yeah, hello there, Rapsu. Such energy you are having today. Very impressive. But why is my workshop door screaming in pain?
No screaming, just door adjusting to reality. Gear must go in. Door was optimistic.
Optimistic? Yeah, maybe in Stockholm, but this door was perfectly happy before you attacked it with industrial enthusiasm.
Gear is important. Big sport gear makes machine happy. Door is secondary system.
Secondary system? Yeah, but listen now, my dear dinosaur friend. This workshop is not sauna. Holes are not feature.
I make ventilation, fresh air, very healthy, Finnish design principle.
Healthy. We are in Finland, Rapsu. It is -20. Now machining is extreme sport. I will need 3 jackets and emotional support mittens.
No problem. Proper clothing, wool, overall, maybe hat. Machining builds character.
Yeah, character and frostbite. Both very much included. In Sweden we prefer comfort and doors that remain door-shaped.
In Finland, if thing almost fits, it fits. Door learned valuable lesson today.
Yeah, you Finns and your situ. Always pushing until something breaks. Usually the environment.
But gear is inside now. Mission success. Door still works. Mostly.
Yeah, mostly. Like Finnish summer. Short and not that much snow.
Exactly. And now workshop has Arctic airflow upgrade. Free of charge.
You are impossible, Rapsu. But yeah, I must admit, the gear is very beautiful, like modern art, but with teeth.
Thank you. I push with pride.
Come now, let us drink something warm before my eyelashes freeze. Next time we measure first. Yeah?
Maybe.
Yeah, that is the most Finnish agreement I ever heard.
Hello! Well, in this episode of Finno-Greek Machining, this episode will be a little bit shorter than always. We are going to go through threading. Threading with a Weiler Matador lathe. This is really specific to this lathe, and first of all I'll go through some mathematics with the threading. Well, not mathematics, it's just tables and stuff. And metric threads. We are not going to go into imperial or Whitworth or whatever threads there are. Just normal triangle shaped threads and with metric. And we are going to go from M3 to M something. And some principles thereof. And I will supply you with an Excel sheet which you can use to print out any table you want to about the threads. I try to make it such that it's easy to use. Well, there are some tables already available in the internet, so probably this is futile, but just to keep stuff coming. So this is an Excel. And then, what we are going to do, we are going to test the retractable tool holder for this lathe. And this will be, let's see, I haven't been testing it, and it might be a little bit, well, let's see how it works. It might work as well. So now the first thing to do is to go into what is a thread and what should you know about threads. Now, let's take a look inside the guts of this lathe. Well, it's a very simple thing. You just turn this knob and then you can open a door. And there you have it. At the moment we have here a gear which is 84 teeth. And this is 120. And this one is 21 teeth. And as you can see in this table here, there is a table down there, we should have 28 teeth gear here up, which I have here, and then we should have here 72 teeth gear, which I have here. So, and yes, this I bought. It was, the gear was ready, but the hole was not it was 16 millimeters. I had to bore it to 22 millimeters. It didn't have a keyway, and now it does. Okay. So, the first thing, of course, is to try to start to remove these things. And in order to get this right, I believe I need to... No, I don't need to remove this, only that one here. So, let's see now. Yeah. So, there is a screw. But this thing, this one, there is a surprise inside. There is a fuse. And you should be really careful when you are dealing with this one, not to drop anything to the floor, for example. Okay, and now I should also have, yeah, I wipe these clean as I go. There is a keyway. If you look carefully, you might see it. And now if I pull this gear out from here, it stays up. And this is of course the wrong gear. This is the 21 tooth gear, which I don't need. I need a 28 tooth gear here. So, but the key here is very, very special. When you remove it like this, you probably notice, I will show it nearer to the camera so that you can see, there is this little thing poking off. It's made of brass, and this is actually a fuse. You should, this is very easy to drop off that one. So now we have like this. And we should also change that one. So we need to take away. There is a C-clip here. Yeah. This should come out quite easily. This should come out easily. Yeah, they come out easily. You just have to be careful so they don't fly around when they pop off. Okay, it's out. Yeah. And next bit is this okay. It came out like this. There is this clutch in the back side. These 3 pins, they go there somewhere, and these should be, that one. I need to clean it up. Now I need to change that gear as well. And I'm just wondering how to get it all out from here. Okay. Yeah, that should be okay. Yeah. Yeah, now it came out. This is really, there is a key here, and this one. And then we need to push it away from there, like that. And now let's pray that my new gear fits here perfectly. This is always a surprise. It should, but you never know. This is a tight fit, really tight. Oh yeah, okay. Let's see if I hammer it with a plastic hammer. Yeah. Okay. The gear is there using this. Okay. And now we just put this thing back here. Well, it went quite easily there. And now we have this. But it doesn't fit here because this whole bayonet is in the wrong place. So we need to adjust that one. And this is done by loosening, first of all, loosening this. This is a 10 millimeter thing. I hope I could. Yes, I could. Wow. And then I put this gear first here, this thing. And you should be really careful when you put this back. So it goes there like that, and then you put your 28 teeth gear here. And this is really fiddly. It doesn't want to go easily at all. After some filing and especially chamfering those keyway things, I got it now there, and it goes. You should not use force at all here. You just put it there, and it should go. And well, I took it out, and now I apparently cannot put it back. Oh man, this is horrific. But I also found out that it's better to put the upside first and then sort of put it there like, now it doesn't want to go at all. Of course it doesn't. And yes, these parts must be really clean. Now it goes. It feels like that. And it's definitely the key. It's dangling out there somehow. Okay, now it's straight. Man, this is really one of a kind. Thank you, Weiler, for this thing. Okay, now it went. Wow. Oh, what a mess. And then I just put this back with the screw here. Like here. Without dropping anything. So that is now the 28 tooth gear here. And yeah, there is this secret inside there. Well, okay. There is some backslash, like always there. These usually have some, and this has quite a lot. But yeah, and next thing is to put this into that, and let's see how easy it is. This is a 10mm tool. Sorry, I probably will block your camera view here because oh man, this is oh, there you are. Oh. Now let's put this on free gear. Yeah, well, the nice thing here is that once you get it there, you just tighten it tight, and then it well, it's okay. And now this whole bayonet thing can be loosened here, because now we need to put the other gear in here. This one goes into here. And of course it's also, yeah, okay. Okay, there you are. And then we should have this there, and then that one, little C-clip there. Oh, these are always one of a kind things. I don't know how to put them back so that you don't damage yourself. That way. Oh, it went quite easily this time. Now, this whole thing goes to here, like this, and now oh, I think I succeeded on the first try. There you are. Gears have been changed. The biggest hurdle was that, which is really, I would say, really cumbersome. But I think they are really good. Okay, let's close the lid. What a... So, the following presentation is about metric thread standard. And here is the agenda of it, and it will be quite a long thing, and we'll be dealing with many things. And we this is just to present the whole thing about metric threads. So let's start, so we don't spend the whole night with this one. So what is the metric thread standard actually? Well, it's an isometric thread, also named like that, and it is the most widely used screw thread standard or system in the world. You can find it almost everywhere, even on countries where imperial systems dominate. Of course, because for example, if a car is manufactured in Japan, then it's exported to USA. Well, it has a lot of metric nuts and bolts in it. So they don't make separate imperial cars for USA. Yeah, okay. So this is one thing. Okay. And actually this kind of a standard it defines how the nuts and bolts fit together. It makes sure that the parts manufactured by different manufacturers are compatible with each other. Yeah, that's very important. And the key characteristics of this standard are it uses millimeters for all dimensions, therefore metric. The thread angle profile is 60 degrees included. And it is defined by several ISO standards. It's not just one standard, it's many of those. And they are listed down there. So, well, to understand these threads, these metric threads, there is some terminology, and this is actually it coincides quite a lot with imperial threads also. So there is a thing called nominal diameter. It is the diameter which you can measure on outside of the bolt with calipers. If it reads a little bit below 10 millimeters, so it might be M10 bolt. But actually this is something that is not a reliable way of doing this. You should also measure the thread pitch, which is the next thing. In imperial threads you define the pitch by so and so many threads per measure unit, and the measure unit in this case is inch. So for example 8 threads per inch. But in metric threads you define the distance between thread peaks. So for example M10 thread, the distance is 1.5 millimeters, thus it will be M10 x 1.5. Oh, as simple as that. Then we have two types of threads. We have external threads, where the thread is on the outside of the thread, on the outside surface, and the internal thread which is inside the hole. That's it. It's those two types of threads exist. And then there is a certain designation system for metric threads. First of all, there is a big capital M in front of it. Then there is this nominal diameter, which might be 8, 1.5, 3, 4, 5, 6, and so on. And then a letter X, and then the pitch in millimeters. And then we might also have this slash and or dash, whichever that, the minus sign. And then we might have the tolerance class. And the most usual tolerance class is 6G for bolts and so on, and 6H for internal threads like nuts. And if you omit the pitch and also the tolerance class, for example, you say that this is M10 bolt. It means that it's M10 and it's a standard coarse pitch with 6G tolerance class. So those are the default values, so to say. And now the thread geometry and shape. As I think I already said it, but yes, I say it again. It's triangular profile, and the included angle is 60 degrees. Period. And then it has some flats on top and bottom root and on top of threads. And especially the root has a flat in there, because sharp corners create stress points. And now if it is rounded or there is a flat, it makes the bolt more robust. It takes more load. It doesn't break so easily. And then we have some important diameters, which are major diameter. This is the diameter, as I said, you can measure it on the overside of a bolt with a caliper, for example. Then we have a pitch diameter, which is something that is not easily measurable. It is so-called pitch diameter, which is in between the peak and the grooves root. It's somewhere in between there. Then we have the minor diameter, which is the smallest diameter of the bolt and the largest diameter of the smallest diameter of the nut as well. Yeah. And however hard it is to measure, the pitch diameter is the diameter that is most critical for a proper fit. And this is the reason why when you are a single point threading, for example, you try it with a nut, because it's not very easy to measure it. So it's sort of you try it out. Yeah. Okay. And here are some. This is just to support this what I was talking about. You can see the flats there on top and bottom of the threads, etc. You can also see how the pitch is defined here, and so on. And this picture was taken from Wikipedia, which is probably the most usable site when you are trying to understand the metric threads. Then there is another aspect on threads, and this is not only for metric threads, this is also for imperial threads. This is tolerances. And why the tolerances are needed? Because it's impossible to create a perfect nut or a perfect screw. You always have some deviation in the dimensions. So tolerances are used to make the parts fit together easily. And there are several tolerance classes, and they define or control how tight or loose the fit is. If it rattles, it's a loose fit, and if it doesn't screw in when there is a hint of dirt, then it's a tight fit. So the optimal is somewhere there in between. Then they define how accurately they are manufactured. When you create a thread, you put the thread in between some tolerances, and there you go. And they also, if the tolerance is really tight, the assembly becomes really a nightmare. For example, if you have a tight thread which the outer diameter is like 60 millimeters, and if it is a tight fit, and then if the bolt which you try to screw in is a lot warmer than the nut, the thermal expansion could make it so that it won't screw in. Yeah. So what are these tolerance classes? We have a few of them, but the most used, the most usual is the 6G and 6H tolerance classes. And the tolerance class consists of two elements: the tolerance grade, which is a number, and then the tolerance position, which is a letter. And the tolerance grade tells how wide measurement range is allowed, and it's still in that tolerance. And then the position means that which side of the, is it bigger or smaller or something in between. Okay. So, since this 6 was the tolerance grade we chose, this is it's indicating that it's a medium tolerance. So it balances between easy assembly and good strength. If the tolerance is very loose, it impacts the strength of the system. And tolerance grade 6 is if you go to hardware store and buy a bolt, the tolerance is usually 6. It's either 6G, which is a bolt, and 6H, which is a nut. And they are the ones you can buy from hardware store. And in the tolerances, this number, when it's small or lower, then the tolerances are tighter and tighter the lower the number is. And of course, vice versa, when the number is high, it's a loose tolerance. And then this G, it means that it's makes it's outside, it's below the nominal size. So it can be a little bit lower than the nominal size, and how much lower is defined by the tolerance grade. The 6 means that it's something. If it would be 9G, it could be loose or tight or whatever. But 6G is a good trade between good fit and strength. And they are G usually it means that it's a bolt, and it's this tolerance means that the bolts can be made a little bit smaller than the nominal size. And it is such, this 6G is such that it fits with the corresponding nut, even when there is some dirt or coating, for example, zinc. And as said, these are widely available in hardware stores. The grade for bolts is usually 6G, usually. And then this H, capital H, it's the same thing. It's the nut internal threads, and this means that when this tolerance is applied, it makes the things larger. And it starts from the nominal size, and then it can be a little bit larger than that. And this means that when it starts from the fundamental, from the nominal size, and grows a little bit from there. And this produces a clean and accurate internal thread. And again, this 6H is used in standard nuts and tapped holes in machine parts. When you buy a tap from, in Finland you cannot buy taps from hardware stores. There are special places where you can buy those, at least if you want to have a good quality one. So the taps are usually graded 6H tolerance. Okay. And then, of course, you have 6G bolt, 6H nut. And then, this is the very usual combination you have. 6H and 6G. And this provides a reliable assembly. So you can screw it in easily, and there is still no excessive looseness. So yeah, and it provides good load distribution. And this is also the default choice when designing mechanical things. Sometimes you need to have a little bit tighter tolerances. For example, measuring instruments need to have that. And some steering components for cars also need to have tighter tolerances. And for example, in micrometer we have a very fine screw, and this one has very tight tolerances, I believe. So, what we have been chatting in this presentation is about metric threads. They use millimeters and a 60-degree profile. That's the thing that they are. And dimensions are calculated or derived from nominal diameter and pitch, period. 6G is used for external threads like for bolts, and 6H is used for internal threads like nuts. And together these two tolerance classes provide a standard, reliable fit. Of course, my presentation was not complete. I present you here a very good site where to start if you want to dig into this subject. So please visit Wikipedia, this page. It's really, really good. It contains a lot of links which you can follow to sites, and it has a lot of information in one page. It's very concentrated. yeah, just to show that. And this is the place where I have read most of the information I have been sharing with you now. Then, just right after this presentation, I will present you a tool I have made. This is actually an Excel sheet which you can use to, well, it calculates thread parameters for you for machining. It has, but more about that after this presentation. And yeah, okay. So now this quite lengthy presentation is over. It took over 22 minutes even. Man, a lot of talking for me. Okay. So next, let's go to the Excel sheet I have made for this thing. So here is the Excel I have made. You can open this, well, it's not Excel, it's actually open created with OpenOffice. You can also open this with LibreOffice Calc in both programs. It works well with both of them. And this Excel sheet, I will talk about Excel sheet because it's, well, I have been used to that word. So it uses macros. And for that reason, you have to enable your macros in here in options. You go to the security and macro security. Usually in these programs the macros are disabled. So, well, I have put low, which is not recommended, but yeah, medium. Then it will ask you whether you can run this macro. I don't know whether it asks every time, but yeah. And then high, and all, I need to sign my macros, and I cannot, I don't know how to sign them. And very high means that it doesn't run the macros at all, and this is actually the default setting. You need to change this to either high, either medium or low in order to run this Excel. Okay. So, what this does? Well, first of all, it has a list of data in this. There you can see that we have a lot of threads here, different threads. These are standard threads. Yeah, and they are defined by diameter, pitch, and classification fine. Then there is an alternative fine and coarse. And then we have some standards like ISO 262, which is the normal metric standard thread. Then we have an old DIN 13, which is also metric thread, but it's like obsolete. And then Japanese industry standard. This is something very special. You might stumble into those sometimes. So, yeah, okay. But you could use this table as such, but it's very cumbersome and not very easy to use. So, let's go back to this one. There is a nice picture which I have stolen from Wikipedia, and it defines all the different parts of the thread, etc. And then this part here, the rightmost, we have numbers here like 1, 2, and 3. And these are like first you should do this, then you should do this, and lastly you should do this. But Actually, you can feed in thread dimensions also totally manually. For example, let's put here 1 millimeter. That's the pitch. And then let's say it is like 9 millimeter nominal diameter. And now it calculates the external thread parameters here. You can also put the same values here on the other side. 9. So you can, these are like internal parameters, and you have here nominal diameter, major diameter, pitch diameter, and minor diameter. And these are here, major is this line here. Then we have the pitch diameter, which is here in between. And then we have the minimum diameter, which is here under. Okay. But so you can feed in whatever you like into those. Please enter numbers. But then we could also select, for example, filter by diameter. Let's go here. So it gives you a list of standard diameters. Let's take 8. This means 8 millimeters. And then I can select from here. I can select, these are all now M8 threads. Different pitches. And we have one GIS and 3 couples of M8 standard threads, and there is an alternative, for example. I took the alternative now. And as you can see, it replaced those values here with the ones I chose here. I can also take the coarse here, and now it's 1.25 the pitch. So it chooses the parameters from here to the lower table and fills the rest in. And there you can then you can do whatever you do with those figures. It also has these 6G and 6H tolerance, minimum and maximum. This is actually quite usable when you do something like with this. And then you can filter by pitch. For example, we can see which threads do we get if we select 1 millimeter pitch. So we have M6, M7, M8, M10 are available with this pitch. Yeah. And then we have a class here. This is not the tolerance class. This is different. This is fine. For example, we can take all coarse threads here, and then let's see. We have all coarse threads here, and it becomes a long list. But how would I use this? If I want to identify a thread. So I would take my calipers, measure the outside, okay, it says 7 millimeters. Okay, let's see, 7 millimeters. Here in the list, we might have 7, yeah, there is a 7. And then I know which standard threads are available for that one. So 2 are available. Yeah, it's actually fine. Yeah, M7 is available. So yeah, okay, that's it. That's about this. You can figure out yourself how to use this. And of course this Excel, which is here, this metric thread ODS, this is available in my Google Drive, and there is a link below. And this also the previous presentation is available there. It is this metric thread presentation ODP, and there is a link below. And if you want to know about, there are a lot of macros in this one. Well, I'm a programmer in profession, so I have been doing all sorts of programming, a lot of. So of course I created macros into this Excel. So they are also there, linked below. So that's about the Excel and how to use it and have fun with it, actually. Okay. Well, I have one more Excel for you, and this is a graphical representation of Weiler pitch settings. And well, this is also very Weiler specific and especially Weiler Matador specific. So you won't be able to use this with any other lathe than that. But sometimes the plates, like here, this top plate, which contains all the pitches, the settings, they have vanished or are a little bit damaged so that they are partly or totally unreadable. So therefore this might be useful for you if you have a Weiler lathe. So how this works, this doesn't get any simpler than this. First, you choose the pitch you want to cut. So you have here a list of pitches. It's a very long list actually. This lathe can do quite many different pitches, especially if you change the gears in the back. So then you get, I believe, all the pitches for this metric ISO standard. And let's choose one. I had here chosen one, and you probably can see that for 1 millimeter we have two. One is this which has F, Z, etc. This is because when this lever, this SF lever, is in the F position, then the lever, this ZR, can be either Z or R position. The only difference is the speed, how fast your blade is moving. So you can choose one of those. But on the S, if this SF is on S position, then the position of this ZR lever matters. It's a little bit, well, how would I say, it's a little bit cumbersome. Okay, so, and then if we want to see what 2 millimeters looks like, okay. So first of all, there is this, as you can see, there is this string which is a little bit, this actually makes the difference between different 2 millimeter settings. There are many, more than one. So therefore we need this to distinguish between them. Then it collects the data from, we have a data sheet here, which contains all the data about the settings. And so first, then you have here the pitch, and then lever SF, which is this first lever, it should be in S position, and Z for this ZR position. And then we have a lever ABC, which is here under. This is now in C position. Between there is a B and A on the very far right. And then finally the lever N, which is this with a numeric scale, and it should be dialed to 4. And then the gears in the back here behind the door, gear 1 should be 21, and the second gear should be 120 or 127. Both work because they don't change the ratio. When you are threading imperial threads, imperial pitches, then you have to use them both. They are used in combination, this 120 and 127, these gears. And yeah. And finally the gear 3 is 84. 21 tooth gear is probably the best. This combination is probably the best for general use because all the values are on the top plate. Yeah, and so I usually keep this combination because of that. And it's a very rare case when you really need to go and change the gears, and those pitches are for M8 and for M12. Those are the ones that need a gear change here in the back. And then finally it tells whether you can disconnect the half nut or not. Yeah, let's see. For example, 2.60 you cannot. And now it tells keep half nut connected. Well, it's a simple calculation. It divides 6 by this number, this 2.60, and if the result is not a whole number, then you should keep the half nut connected. If it is a whole number, then you can disconnect the half nut. 6 is actually the pitch of the what is it called? Now I have a short circuit in my brain. The lead screw. The lead screw in this lathe has 6 millimeter pitch. Therefore, 6 is divided by this pitch, and then you can see whether you can disconnect it or not. Yeah, okay, and well, that's it. And also this Excel is available in my Google Drive, link below. Yep, and have fun. And next, now we are really going to make an M12 thread, and we are going to use this retracting tool holder to see whether it works or not. See you there in the lathe, by the lathe. So now, this is the moment of truth. This workpiece, I have turned it down to 11.97 millimeters. So it should be very suitable for threading M12 times 1.75 millimeter thread. So now let's take 0.1 millimeter cut. And now I push the thread. Oh, yes. The 6 millimeters, which was the pitch of my lead screw, is not divisible by 1.75. I cannot disengage the half nut, and I'm running this really slowly, so this is now the first pass ever, and it will be a scratch pass. Seems like it's not totally concentric, my thing. And this is actually very nice. Let's turn it like that. And now this is thread gauge. It matches really. So the thread pitch is correct. And now we have to go back. And I will put some cutting oil into that one as well. There you are, I think. Yes. And let's go to 0.5 millimeter right away. This should work quite well. Well, this is actually quite fun. And now the nice thing here is that I don't need to take care of the dials and remember what was the depth of cut the last time. Let's see if it is. It is. There you go. And now let's go to, well, 1 millimeter. This tool is rigid enough. It's really rigid. No trouble at all cutting this. Yeah. Next will be 1.25 millimeters. Yes, let's go. Oh, yaha. When it has load, it jams, okay? That I must now consider. It was really hard to get out. Okay, maybe a scratch pass now. It seems to be a really yeah, this it somehow really changed a little bit tighter for some reason, I don't know why. Yeah. So probably the tolerances in this one are a little bit too tight. So I need to do something for those, maybe. Why is it so tight? Okay, wow, it is tight. So I take 0.1 millimeters now. Well, it becomes looser and looser all the time. It's a loser. This needs some practice, I believe. And now let's take 0.1 millimeter again. It doesn't look tidy. Oh yeah. But the rigidity is, it's there. It's really rigid. .1 millimeter more, and there we go. But there is no rigidity issues, which is really good. There you go. Let's see. I'll take this away and see how our... Yeah, this is really a spring pass now. Maybe one more spring pass. Spring pass. Let's take a little bit. I almost disconnected the half nut. I'll take 500 more here. Just for a good measure. This is by no means a perfect thing now. It becomes perfect when I know, when I catch why is it so tight at places. And this is definitely now the last one. Should I actually try it? There is the file. Yeah, it was all it needed. Now it's really tight. Not tight, but yeah, there you are. A rusty nut goes into a clean, and there is some debris. Yeah, well. It's a good fit, really good. It doesn't wobble at all. That's now the conclusion here. This tool is okay, but it has some difficulties with I don't know what. I believe it is gripping on the underside there. There seems to be something. Yeah, it is not the dovetail that is causing the trouble, because it would be causing it here as well, but it is there under. But I can fix that. That's easy to fix. Take it out and just file away from this workpiece. This should be easy to do. Let's see what we are going to do the next time. Okay, till the next time, bye! Some epilogue here now. Well, actually, now it works all right. It was not the Dovatel issue, it was actually here under. This eccentric was scraping here under. And it left a clear mark where it was scraping, so it was very easy to file that part away. Now, it's probably a perfect tool. Probably. Well, yeah, it needs, there is a learning curve with this one, yes. But it eases in a way that it's easier. You don't need to remember the previous depth of cut. So you can progress very easily and do spring passes really easily. Because you don't need to use the dials to retract the tool, but you can use this one. So you can leave the dials alone. That's very good thing. Okay, now, bye, till the next time.